Hey developers, ever wished scrolling your web page could feel like directing a movie? Like you're the camera operator smoothly guiding a full 3D scene. That's exactly what we're diving into today. I'm a UI developer and I've wrestled with this in real projects. So I'm not just showing you flashy demos. I'm sharing the exact technique I use to combine threejs with GSAP scroll trigger. We'll make your scroll drive a 3D world like a total pro. In this part, we're building the core foundation. From initializing our renderer and camera to loading and perfectly framing our 3D model. You'll learn professional techniques for centering objects, calculating ideal camera distances, and setting up the animation heartbeat that brings it all to life. When this video hits 200+ likes, I'll pin code link in the comments. Your support makes these deep dives possible. Let's walk through this code together, line by line, starting with our container declaration. We grab the div with ID equals webgl using document.getElement by ID. This container will host our entire 3D scene. Think of it as mounting a movie screen on your web page. Next, we initialize our webgl renderer. The renderer is our engine that draws everything onto the canvas. We pass it in configuration object with two critical parameters. Anti-alias equals true enables edge smoothing to prevent jagged lines, while alpha equals false gives us an opaque background instead of transparent. Why opaque? Because transparent backgrounds require extra GPU computations that can slow down performance. We then set the pixel ratio using renderer.setPixelRatio. Inside this, we use math.min to cap the value at 1x maximum. This prevents high-density retina screens from rendering at 3x resolution, which would murder mobile performance. The window.device pixel ratio, or 1, acts as our fallback for browsers that don't support this property. Now we define our color space with renderer.output. Color space equals 3.sRGB color space. This ensures colors appear natural to human eyes, mimicking how physical screens display light. We append the renderer's canvas element to our container using container.appendChild. This physically places our 3D canvas in the DOM. For initial sizing, we call renderer.setSize with two parameters. First, container.clientWidth or window.innerWidth. This uses the container's width if available, otherwise falls back to window width. Second, the same logic for height. This ensures we have visible content even during initial page load. We create our scene with new 3.scene. This is our virtual room where everything exists. Then we initialize a perspective camera with 4 essential parameters. 50 degrees field of view matching human binocular vision. Aspect ratio calculated as container width divided by height. Near clip at 0.1 and far clip at 1000. Adding camera to scene makes it part of our world. For model loading, we define model URL pointing to our GLB file path. The GLTFLoader instance will handle loading this 3D asset. We declare model as null initially since loading is asynchronous. Model size is a 3-dimensional vector and look target fixed at world origin 000, where our model will eventually center. Inside loader.load, we first process the loaded model. We assign GLTF.scene to our model variable, then traverse every child object. For each mesh we find checked with o.isMesh, we set cast shadow equals true. This enables shadow casting for realistic lighting later. We add the entire model group to our scene. Now comes precise model positioning. We create a bounding box around the model with new three.box3.set from object. Box.getSize populates our model size vector with exact dimensions. We calculate geometric center into a new vector using box.getCenter. Then center the model at world origin with model.position.subcenter. For camera distance calculation, we create a bounding sphere from our box. We get its radius with math.max against 0.0001 to prevent division errors. Convert camera's vertical FOV to radians using 3.mathutils.deg to rad. calculate vertical fit distance as radius divided by tangent of half vertical FOV, calculate horizontal FOV using camera aspect ratio, then horizontal fit distance similarly. Our final fit distance takes the larger value multiplied by 1.5, adding 50% breathing room around the model. We dynamically set near clip to fit distance divided by 200 minimum, 0.01, and far clip to fit distance times 200. These prevent clipping during animations. Camera.update projection matrix applies these changes, and camera. Look at 000 points it at our centered model. After model setup, we call three functions. Add floor and shadows passing our bounding box. Add lighting for scene illumination, and build scroll timeline for scroll-driven animations. These will be detailed in upcoming videos. Finally, we start the render loop with a self-executing function. This runs continuously at 60 FPS. Camera.look it maintains focus on our target renderer. .render draws the updated scene, and request animation frame keeps the loop alive. The undefined parameter in loader.load is our progress handler unused here, and the error callback logs failures to console. That completes our deep dive into the core 3D setup. We've covered everything from renderer initialization to precise model framing. In our next video, we'll implement the shadow system that grounds your objects, professional lighting techniques, and the scroll-driven timeline that brings Hollywood-style camera moves to your webpage. If this breakdown helped you understand three.js scene setup, please smash that like button. When we hit 200 plus likes, I'll share the full source code. Subscribe for the lighting tutorial where we'll make materials shine like real products.